Yeah, in this chapter, we will talk about mass balances, which are certainly the basis for every bioprocess. Yeah, welcome to the part mass balances. Mass balances are certainly one of the basic things you always need to do if you want to set up a bioprocess. Essentially, if you want to produce 1 ton of your metaboli, let's say antibiotics, you need to know what to put in. You need to know what's running there in order to scale your process, in order that you can calculate at the end your economics and so on. So therefore, this is something what you will have to do always. Now, the basis of this chapter, as already recommended at the very beginning, is the Bioprocess Engineering Principles, second edition of Pauline Doran, the second edition in academic press. I warmly recommend you to also have a look in this book. The examples are taken out of this book because the good thing is that the solution paths of these examples are also in the book, and it's, if you do it at home, it's a wise idea to check it. Maybe a general remark how to solve exercises is, don't start with looking in the solution, even though for these examples you have a solution path. Start first with trying it yourself. If you just read the solution, everything looks simple, but if you do it yourself, you then realize where you have difficulties, and you can work on these difficulties, and you need to train yourself in getting a certain speed in solving exercises and a certain strategy, and this you can only do if you do it yourself and not looking others in solving exercises. So material balances, we look at 2 different aspects. You see that balancing bioprocesses, as I said, we have 3 parts. We have material balances, we talk about energy balances, and we will at least look how unsteady state balances look like. Unsteady state balances will then go also in the kinetic session, so we will not talk in this context too much about unsteady state balances. Again, we start with mass balances, and we then go to stoichiometry. So after this section, you should simply know how to set up material balances and be able to solve simple mass balance problems. Okay, of course, if you have a fermentation process, this process must be designed with respect to material components like the substrate, product, cell mass, and with respect to energy. In general, for a bioprocess, this means that you need to cool. Of course, bioprocesses are exothermic reaction, although you usually see, if you are in the lab, you have the things on a stirrer in a heater. You have it at an incubator with 37 degrees. The reason is simply because there is in the most part of the time nothing inside. So if it's an exponential growth, you have it at the end. But in a large bioreactor, this, of course, a growing microorganism produces heat, and you need to remove the heat. That is like if you run in the forest, you produce heat, and you need to remove the heat. And the same is true for bioprocess. But again, we start now with the material components like substrate, cell mass. So therefore you have to design the overall process via material balances and energy balances. That's the very basic. So if you want to set up a process and you know I need to produce 1,000 of kilograms of my product per year, then you need to balance the overall process. You need to know how do I need to size then at the end the equipment and so on. And that's the first step in such a setup. Now, let's come to an example. Now, let's assume you have a process looking like this. This is the nice thing always if you talk about material balances, we start with a system. So this is our system. This comes from thermodynamics. So this is our system doing things. And then we assume we have a stream in and we have a stream out. And in the stream in, this is mass in, kilogram glucose. So we talk about a process where we put glucose in the process, and then we don't know what happens in the system, and then glucose comes also out of the process. M out, kilogram glucose. So that's very simple. So we have at the end, we balance our in glucose and we balance our glucose out. So now we measure the concentration or the mass of glucose going in and the mass of glucose going out. And now we realize that M in is not equal to M out. And my question to you is now, what could be the reason that M in is different to M out? Be it higher, be it lower, and you measure a different concentration at these positions. So it's not the same. Okay, so there is one response here, because it could be converted to the product or consumed by a microorganism. Yes, the glucose is consumed by a microorganism, for example, in the system, and then you have less inside. This is in general what we want to have in our bioprocesses. Production of other products in the reactor, this is very general. It could also be that it's a reaction which is not due to the microorganism, which is a side reaction. It's not a closed system. Lost. This could also be a possibility. The system is leaking. It might be that something drops out of our system, that here our glucose is leaking out. We don't see that. And therefore, we have less glucose coming out. This could be a reason for M in is not equal to being M out. Glucose consumed, glucose accumulation within the system. This could also be a problem. So if you measure, then you have a lower amount of glucose getting out. It could be for whatever reason that your glucose crystallizes, and then you have here crystallized glucose, and the out is then lower, and this glucose is not being consumed. You have no window to look into the reactor. This could happen. And this is a very important statement here. The measurement could be wrong. Very frequent reason is you simply did not adjust an appropriate measurement. Maybe your measurement system is not suitable. Maybe the measurement range is not correct. Maybe you asked someone doing an internship to do this measurement, and he has no idea how to use the equipment. For us, of course, let's say a biochemical reaction in between is what we want. So usually if we talk about bioprocesses, we put in glucose and we want to have our microorganisms to metabolize the glucose and produce biomass or produce ethanol or whatsoever. However, despite the fact that's what we want, it's not necessarily the case that the glucose is consumed in this process. It could be other very banal reasons, like the system is leaking, it's enriched in the reactor, or very simple, the measurement is wrong. And we are talking here about engineering. It is very, very, very important that you have these potential problems in mind. So if you start your calculations, you have to assume that the measurement is correct. You have to assume that the system is not leaky. Because if you have to assume it, that means you didn't check it. If you're an engineer and you work at a different site and you get the results of the measurements from someone, and you didn't check whether the system is leaky or not, then before starting your calculation, state, I assume the system is not leaky. In other words, this means you didn't check it. Because if your result is bizarre at the end, you can go back to your assumption and realize, well, I didn't check that. Now, as we have such a bizarre result, we don't go for the novel committee that we have found a process that Escherichia coli produces glucose. We might first check whether our measurement is wrong. Yeah? And then we have to do that. Yeah? And this is very, very, very important to put these assumptions. Assumption means you didn't check it, but this could interfere with your result. And for each system, you have to think yourself, what could interfere with the system? Okay. This is what we have talked about, and we have talked about possible reasons. And of course, the consummation by a reaction within the system is what we want to see, but this is not necessarily the reason for it. In the more general term, if we put mass into the system, the mass of this compound, or the total mass, will increase. If we take mass out, it will decrease. And if the mass accumulates, then of course it will either in or decrease depending on what's happening. And if the mass is consumed, it will decrease. And if the mass is generated, it will increase. And this is and very simple. So of course, then you can say my mass which is accumulated at the end is my mass which gets in the system minus my mass which gets out of the system plus my mass which is generated minus my mass which is being consumed. So M accumulated is equal to the mass which goes in plus the mass which is generated minus the mass which goes out minus the mass which is being consumed. Okay, so this is the general mass balance. Now, very simple. So that's very logical. Assuming that the system is not leaky, assuming that there is no that there is no accumulation like this in the system. So only in this case, of course, this is valid. Now, in many systems, what we have is a steady state. So a steady state means that nothing is accumulating in the system. It's, of course, if you have a system where you have accumulation, you will have to stop the system. So, of course, in a batch bioreactor, things like this happen. But if you have, if you want to run your system for a longer period, then, of course, you don't want to have an accumulation. So the M accumulation is equal to 0. And in this case, if this is set 0, then you come to a new form, and then you have M in plus M generated is equal to, I'm just rearranging, this is 0, and is equal to M out plus M consumed. So this is system without accumulation. Yeah. And now, if we have a system where there is no reaction, in a system with no reaction, we come to an equation which looks even simpler. In this system, we have the M generation is 0, so M gen is gleich M is equal to M consumed is equal to 0. So in this case, the mass balance is simply M in is equal to M out. So this all looks very trivial, and in principle it is. It is not complicated, but you will see later on, if we start with our calculations, always if we see now this M in, if we can write down an equation M in and out, we're very happy, because this is then usually the first thing we can use for solving mass balances, and our starting point for this. So now coming back to the slides. Okay. So we have set up the mass balance, and we have said that we could simplify it in a certain system. Now let's come to the first example. Now in this example, we have a continuous process for wastewater treatment. So the in and the out streams are like this. So we have a wastewater feed stream. We bring in 10 to the 5 kilograms per day cellulose and 10 to the 3 kilograms per day bacteria. We have a clarified water effluent stream. So 10 to the 4 kilograms per day cellulose go out, 1.5 times 10 to the 4 kilograms per day bacteria go out. And the accumulation, generation, consumption rates are like this. The bacterial cellulose digestion rate is 7 times 10 to the 4 kilograms per day, and the bacterial growth and death rates are 2 times 10 to the 4 kilograms per day and 5 times 10 to the 2 kilograms per day bacteria are lysed. And the question is there an accumulation of bacterial cellulose in the system? Calculate. This question now goes to you. you at the computer calculate. So what you do now is you do the calculation for bacteria, for cellulose. As soon as you have the result, you put it in the chat window, and of course we will have then a look on the solution all together. Yeah, here we have a response. So it's 5.5 times 10 to the 3 of bacterial cells per day. And this is for the bacteria, which is good. Yeah. 5,500 kilograms per day bacteria. It's the same result. Always use the scientific notion because it makes life way easier. And we have the cellulose accumulation 2 times 10 to the 4 kilograms per day. So that's correct. You can in parallel already start doing the calculation for the complete accumulation and for the cleaning interval, because we have the capacity of the system is 100 tons. I don't think that many of you had a problem, but again, first of all, make a flow sheet. So the system here is also very simple, so you don't really know what's happening in the system, but you have M in, you have the M in, M out, and you have here kilogram cellulose, kilogram bacteria, you have kilogram cellulose, kilogram bacteria. A good idea is always put the mass balance first. So M.Ag, what we have used before. It's a very simple formula. So it's not a formula which is a complicated formula. It's a very simple formula. But don't even simple formulas, don't use that formula again and again and again. This takes time. So in an exam where you will deduce all formulas, it makes no sense. This is why you have a formulary. Just put it, because this also avoids errors, especially with the sign. So it's M in minus M out plus M generated minus M consumed. And now you simply put it for cellulose. So you start with cellulose, and then you put M cellulose accumulated is equal to. And now you can simply copy M in. You say it's per day. The calculations are per day. So then you don't need to put this per day every time. So cellulose, we said 10 to the 5 kilogram per day cellulose go in. 10 to the minus 10 to the 4 kilogram cellulose go out. So now you copy simply the values you have in the exercise here. And the good thing is you don't forget anything. So you have here your M generated and consumed and so on, and you don't forget that you look up whether something is generated in your system. If you find a value here, you will of course put it, but you cannot forget it like this, that something is generated. So nothing is generated, we didn't find anything, so you put here a 0 kilogram. Please don't just leave it out, put a 0. Now this is of course a very simple calculation, but put a 0. This shows you didn't forget to check in the exercise whether something has been generated or not. Remember, at the end you're an engineer, you want to be sure that the response is correct. You don't get a grade for your calculation, it must be correct at the end. If you construct a bridge, for example, you always need to get out with a 1.0, because otherwise the bridge will break down, and this is not an option. Yeah. So therefore you need to make sure that you have everything. So now the consumption rate was it was 7 times 10 to the 4 kilograms. Always use the scientific notion here. Nobody wants to count zeros. And if you put all together, this is a very simple calculation, then you end up with this 2 times 10 to the 4 kilograms. And of course, this is an accumulation. Yeah, because it's positive. Accumulation. Now we do the same for bacteria. And we have the M bacteria accumulation. And we do the same. We simply copy. So M in is 10 to the 3 kilograms. M M out is 1.5 times 10 to the 4 kilograms. M generated is 2 times 10 to the 4 kilograms. And here we have lysis of the bacteria, so we have also a consumption. Consumption is lysis, is 5 times 10 to the 4 kilograms. And that's equal to 5.5 times 10 to the 3 kilograms. Okay, don't forget, I want to, at the end, it's important, how often do you have to, what is the cleaning interval or the sludge removal interval in days? So we have a solid accumulation here. So M acc total is of course M acc accumulation cellulose plus M accumulation bacteria, and this is equal to 2 times 10 to the 4 kilogram plus 5.5 times 10 to the 3 kilogram, and of course this is 2.55 times 10 to the 4 kilogram. Now per day, so now we can put the per day, that we have the time period again inside. Now I want to hear the cleaning interval from you. I'm still waiting. I hope that not everybody has fallen asleep on the other side. Around 4 days. Yeah, so this has been rounded to 4 days. So the question is that correct? So let's calculate that together. Always put it in a formula. The cleaning interval is the so T cleaning, that's the capacity of the system divided by the accumulation rate. So it's 100 tons divided by 2.55 kilograms per day. Now 3.9 days we have. I want to hear it in full days. So we have now 4 days, 3 days. So you should put full days. 3.9 is the mathematical correct value, but you don't. In such a system, you come each day. Yeah? You run the system, and then an operator has to come, and he comes all 3 or all 4 days. So the question is, does he come all 3 days or does he come all 4 days? So important here we have tons, and now the most important thing is for all these calculations is how to convert correctly. So a ton, 1 ton has 10 to the 3 kilograms. So 10 to the 3 kilograms per ton. So this here is the most essential thing in the complete calculation. This is this conversion, and always do it like this. This is my recommendation, because here you see that my tons are throttled out and that the result must be correct. So we end up with 10 to the 5 kilograms divided by 2.55 kilograms per day. And if you calculate that, you end up with 3.92 days. And now, of course, you were asked, again, look at the question. You were asked to state in which interval full days sludge has to be removed. Full days is not 3 to 4 days. Full days is 3 days or 4 days. Now, usually you would say, I will round, yeah? And that's exactly the case here. Ms. says 3 days, otherwise the system is stuck. So in this case, you cannot round to 4 days. 4 days, it's wrong, because your system will be overloaded, and you cannot do that in this case. So your job as an engineer here is also to think about the correct solution. 3.9 is of course the mathematical correct one, but if you have to come every day, you have to clean it each 3 days and not each 4 days. This is the correct solution. Looking again at our first example, we have finally solved it, and most of you had the correct solution. So we calculated the cellulose accumulation, the bacteria accumulation rate, we put it here per day, so we didn't have to put always the per day. And overall, the solid accumulation rate then was 2.55 times 10 to the 4 kilograms per day. And therefore, the cleaning interval was 3 days. Remember, not 4 days, because otherwise the system would be full. So it's not just mass, it's also thinking about what to do. Now, if this was the simple glucose example, we had said in the mass balance, often you don't have accumulation. So you are in a system where you have a steady state, so where you steadily bring something in and bring something out, and there is no accumulation in the system. So in this case, as we have already shown, M accumulation is 0, and then the equation turns to the simplified form: M in plus M generated is equal to M out plus M consumed. And in the absence of a reaction, you get then M in is equal to M out. This is not only true for masses if there is no reaction. This is always true for the total mass in a steady state, and this is of course also true for atomic species. So you don't generate in a biological reaction carbon or nitrogen. The elemental balances are always M in equals M out. Now we had of course a very simple balance at the beginning. We start simple, but of course if the processes get more complex, also the balances and the demands for solving the balances get bigger. What is essential if you want to start to solve more complex problems? The essential points is, first of all, generate a clear process flow diagram showing all relevant information. So this is something which is really important, because this visualizes the process, and my experience tells me that people who failed to set up a flow diagram which makes sense also fail then later on in doing the calculation. If the flow diagram is correct and appropriate, then usually for the people it's no problem to solve it. So really take care about that and make this clear. Now the second thing is select a set of units and state it clearly. So what you have to start and the basis for calculation, and set it clearly. We'll come to it what it means, and of course state all assumptions applied to the problem. This is very important. I said, for example, we assume that there is no leakage. We assume that there are no gases in the liquids, for example, which usually you can neglect, but not always. And all assumptions you put in for your calculations to do, and assumptions are okay, but it's important that you state the assumptions. And then finally, of course, you identify the components which are involved in the reaction, because then you know what mass balance you can apply, because all components in the reaction, you can have a generation or consumption of the components. If it's not in the reaction, it's just M in and M out. So this is something you should collect at the very beginning. So how is the procedure to set up a mass balance calculation? First of all, you just assemble everything that you need for your calculation. So you assemble and you generate your flow sheet. If you want to do it with systems boundaries and so on, you say data and units. So you say, I always work with kilograms and so on. So you bring everything to the same unit. And then you analyze, you state your assumptions, you collect and state extra data needed. For example, you might need densities or whatsoever. Collect that in this step. Then you select the calculation basis, for example, kilograms per day, and then you don't need to state it each time. You list the compounds involved in the reaction and appropriately not in the reaction. You write down the appropriate mass balance for each compound, and then you start your calculation. Set up the calculations with a table where you have all components and streams. You will see in the next example how this is done. This is just the general cookbook how to set up a material balance. Calculate the values, applying your mass balance equation, and check whether the results are reasonable. It's very important that you do it really step by step. The mass balance thing you will see, especially if you try to solve example 4, is a lot of writing. You write a lot, but it's important that you really really write out what you actually do and write down the mass balance, even if it's trivial, even if it's your mass balance is m in is equal m out with your total masses. It's of course obvious that if you put 1000 kilogram in your system and you're in a steady state, that you will get out 1000 kilogram. So in principle, you think you don't need to state it, but do it, because this makes then the complete calculation path clear. Of course, in the exam, you have to do it anyhow, but this is also important for you, because if there is an error and you don't clearly state every step, you have no chance to identify where the error is. And remember, at the end, you don't do this balancing for the exam. This is an engineering approach. It needs to be correct, and you need to make sure that it's correct. And finally, answer the specific question and state the answer clearly. What is important is do it step by step, do it serially. Don't start, if you collect the assumptions already, with doing calculations. This is the most important suggestion I have for you, because then you reduce the complexity of the problem. The main beginner error is that you think, wow, that's easy, so I do two things at the same time. The problem is, with this approach, often you forget then something. You overlook that maybe the bacteria also lysed, and then this term is missing, and then your result is simply wrong. And you need to come up with a correct result. Do it step by step. And ideally, the calculation later on, you don't think. It's you shut down your brain and you just do it. So it's like you want to come to a stage where you don't need to do complex calculation, where you just can calculate it down. You write down the mass balance and you calculate it down. And that's then good, because then you don't make errors. If you have to think too much about every step, this is not good. And this comes with routine. So this is something, therefore, you need to do it a couple of times. Yeah, so at this point, I want to thank you very much for your attention. I wish you a nice day, and I hope that you enjoy the weekend. Goodbye.